We're really, really lucky to have Salil Vadhan here today. Genuinely really excited to be on a session with Salil. Briefly, to give Salil's bio to you before sort of saying how the session will run. So Salil is the Vicky Joseph Professor of Computer Science and Applied Mathematics at the Harvard John A. Paulson School of Engineering and Applied Sciences. He's the lead PI on the Harvard Privacy Tools project and co-director of the OpenDP open source privacy software project. To list some of his accolades, he's Simmons Investigator and ACM Fellow, has received a Guggenheim Fellowship, a Gödel Prize, and a Phi Beta Kappa Award for Excellence in Teaching. So Salil really is an expert to have in our presence. Briefly to say how this is going to run, Salil's going to run through a presentation for about 15, 20 minutes. I'm then going to humor myself largely by asking Salil some questions which my angle is very much, I am a mathematician, I understand DP to an extent, but I'm going to ask questions which I think don't get asked enough of the theory people from the sort of model policy-facing side. So that's the angle. And then we'll open the floor to any questions that everyone else has. So I'll hand over to Salil. Thank you.
Thank you, Owen. Thanks for the kind introduction, and Jack and company for the invitation. It's great to be here. Wish I'd been able to be here yesterday, but I already have enjoyed what I've seen. I'm going to try to be brief in this presentation portion, really view it as a kind of level setting so that we're all talking about the same thing before we dive into the Q&A. Goal is to talk about what are the opportunities and challenges around differential privacy, but the presentation will focus mainly just on what the basics of what differential privacy is. Okay, so differential privacy is, of course, a privacy-enhancing technology with utility and privacy goals, like all privacy-enhancing technologies. The utility goal is to enable statistical analysis of data, and the privacy goal is to protect individual level data. Okay, make sure that you can allow you to reveal information about the population like you do in would like to do in statistical analysis, but make sure that individual level information is not compromised. Let me dive in a little bit more detail on each of these. So what do we mean by statistical analysis? So this can include the publication of statistical tables as done often by national statistical offices. It can include publishing the parameters of a trained machine learning model. It can include publishing a synthetic data set. These are all included in the scope of differential privacy. And it can also include something that came up in the previous panel discussion, mediating access to a sensitive data set through some sort of a query system where analysts who are interested in studying the data set and asking perform a linear regression on some variables of their choosing, issue queries, and differential privacy provides the constraints on the interface to the data to make sure, again, that privacy is protected of the individual data subjects in the data set. Already, these are examples that you probably can't see from where you are, but query interfaces are often already in use as a way of mediating access to sensitive data sets. There are examples from the US Census Bureau. These are all mostly US examples, education statistics, genomic data, and also big tech companies making data available, for example, about web search trends. Why do we need a new privacy-enhancing technology, this mathematical theory of differential privacy, compared to what we've done in the past? And the reason is that it's increasingly understood that the traditional methods for protecting privacy in sensitive data sets are ineffective. So the most traditional approach for trying to protect privacy in sensitive data sets is to strip the data set of so-called PII, personally identifying information. And now there are many, many examples where data sets that have been supposedly anonymized in this way can be re-identified. Individuals in the data set can be, the information that's left there, even though it doesn't look like it's identifying, does turn out to be identifying. One of the first early striking examples that many have heard of is LaTanya Sweeney's example of linking supposedly anonymized medical insurance claims data with publicly available voter registration lists on zip code, date of birth, and sex, and that turns out already those 3 innocuous statistics in the United States turn out to uniquely identify well over 50% of the population. Perhaps more surprisingly, and really kind of motivating differential privacy, is the fact that even what seem to be publications of aggregate statistics still can have very severe privacy risks associated with them. And so this was first shown in theory in the early 2000s by Danir and Nissim, that if you publish enough aggregate statistics on a data set, an attacker can take all of those published numbers and basically solve some big system of equations and reconstruct almost all of the underlying sensitive data, which then can be subject to the same kind of re-identification attacks that we were talking about a moment ago. This was shown in theory and motivated the development of differential privacy, but it's actually also been found to be, these reconstruction attacks, to be effective in practice on the releases. This is what motivated the US Census Bureau to modernize its disclosure limitation and adopt differential privacy, as well as other commercially available systems that were thought to be GDPR compliant. A different kind of attack that I think you all probably heard of in Reza Shokri's presentation yesterday are membership inference attacks, where using published aggregate statistics or using a published access to a published machine learning model, you can determine whether a target individual that you want to attack was in or not in a sensitive data set or in some sensitive subset of that data set. And so this was shown in principle to be possible on genomic statistics that were made available by the National Institutes of Health in the United States, and got the NIH to remove the data or restrict access to many of those genomic statistics that they previously had been making available, because they're being able to tell whether an individual is even in a sensitive data set would attach to them the disease status associated with that data set. So that can just even membership in a data set can be quite sensitive. Okay, so that's what utility differential privacy aims to support. What does it mean by privacy? We won't dive into a formal definition, but roughly speaking, the way in which it tries to protect individual level data is to make it from an attacker's perspective, an observer's perspective, as an individual in the data set, as if your data was not even present. It should be indistinguishable to an attacker whether you were in the data set or not, whether your data was there with its true values or arbitrarily altered values. And so in that sense, every individual's privacy is protected, and yet still signal about the population can come through. The remarkable thing about differential privacy is that it doesn't require making assumptions like many traditional methods for privacy protection about what attack strategy an attacker uses or what other data sets they have access to. And it's increasingly being accepted as a gold standard for privacy protection for statistical analysis of sensitive data. And the way that differential privacy is achieved is we design methods that inject small amounts of random noise into the computations of, into the statistical analyses or computations that are used to produce the models or statistics that we publish. This small amount of noise is enough to, again, hide the effect of each individual data subject. Each person's data is hidden, yet again, still we allow signal about the population to come through. All right, this leads to what's known as the privacy utility trade-off. So part of the theory of differential privacy is that every time you make a publication on a sensitive data set, a statistic or anything you release, it incurs some amount of privacy loss to the individuals in that data set. And we can tune this by how much noise we introduce in the computation. The more noise we introduce, the less privacy loss is incurred. But of course, we have less accurate, and we pay a price in utility, less accurate statistics that we're publishing. And if we put in less noise, we will have a greater level of privacy protection, but of course, more benefit is more accuracy. And it's known that this trade-off becomes less stark as you work with larger and larger data sets. And that as your data set size grows, the impact that you need to achieve a given level of privacy protection is kind of vanishing compared to the impact that's already there from the fact that all of our data sets are samples and we have statistical uncertainty in any kind of statistical computation we do. All right, so one remark I put in parentheses here, the phrase inherent. This privacy utility trade-off is often, and we heard it a little bit in the previous panel, is thought of as a limitation of differential privacy. But the way I see it, it's not a limitation. This privacy utility trade-off is inherent. It is inherent in making any kinds of analyses or publications on sensitive data. We know this because of the attacks and both theoretical and practical attacks that we've seen on data releases, that it is impossible to extract unbounded amounts of utility from a sensitive data set without eventually paying a price in terms of privacy and being vulnerable to actually quite severe privacy attacks. And so what differential privacy does is confront us with this trade-off, which can often be lead us to kind of uncomfortable choices between are we willing to take this price in utility? How important is privacy compared to utility in this application? So one aspect of this quantitative theory of privacy loss that differential privacy gives us are what are called composition theorems that tell us how privacy loss accumulates when you release more and more statistics. And this is kind of really important and something that is kind of missing maybe from some of the traditional ways of thinking of disclosure control, that allows us to reason, when have I published too much? Okay, when do I stop publishing statistics to make sure that I don't, again, become vulnerable to these kind of reconstruction and other sorts of attacks? And much of the research literature on differential privacy has been to try to improve the way these composition properties so that we can squeeze as much utility as possible while maintaining our desired levels of privacy protection. Okay, and the kind of recommended use of differential privacy is to kind of decide what is the level of privacy protection you're willing to tolerate, privacy loss you're willing to tolerate, and then make sure you stay within that budget. Okay? And one way of thinking of it is, again, differential privacy is exposing and allowing us to think about quantitatively this accumulation of privacy loss. Trying to ignore that is like driving without a meter to tell you when you're about to run out of gas. Okay, and we don't want to be driving blind and not know when we are reaching that danger point on privacy protection. Okay, so very quickly, it's worth just contrasting differential privacy with other privacy-enhancing technologies. Of course, very basic cryptography is basically good for protecting data when it's at rest, when you're not using it. Okay, making sure that there's not unauthorized access to it, so encryption and authentication. Some of the others that are being discussed in this conference: secure multi-party computation, trusted execution environments, homomorphic encryption, federated learning. These are, the way I think about them is they are preventing leakage of information during the process of computation and allow us to avoid trusting one party to hold all of the sensitive input data. And kind of the pictures I had at the beginning for differential privacy, the most basic model for differential privacy is where you do have a trusted party that you can hand all the data and let them implement the methods to introduce noise and produce the publications on the data. And differential privacy, to contrast, so these methods are for protecting leakage during the computation. Differential privacy is the one privacy-enhancing technology that's really concerned with what is the leakage from the outputs, the things that you're actually going to publish or release to analysts or to the public, and making sure that those don't, again, reveal individual level information. It's complementary. It's not in competition with the other PETs, and ideally, it can be combined. It's combined with the above approaches when you don't have a trusted party that you can hand all the data. So again, this is the basic model of differential privacy. A trusted curator has all the sensitive data and makes publications or answers queries on it. There is what's called the local model for differential privacy, where where the noise is introduced at the endpoint of the individual data subject, like on your phone or web browser, before it's sent to the centralized curator that's doing analysis on it. There's a big price and utility to work. It provides a stronger privacy model because you're protected even against the organization that's collecting the privatized data. But there's a big price and utility for local differential privacy, and so that's another motivation for, instead of doing just basic local differential privacy, combining differential privacy with other PETs. And then something that's intermediate is I'm sure you all have heard of federated learning. You can think of federated differential privacy as something intermediate between the two. There is a huge literature of basically, at least in theory, showing that pretty much everything we do in data science and machine learning, statistical analysis, is in theory compatible with differential privacy. This is from about 10 years ago. There was already a long list, and it's really exploded since then. And there have been many exciting deployments of differential privacy. Most prominently, the US Census Bureau is using it for all of its public use products from the 2020 decennial census that happened a few years ago. But there are also deployments by all of the major technology companies, and a growing ecosystem of startups and privacy technology providers incorporating differential privacy into their offerings. It was used during the pandemic by the big tech companies to make, for example, mobility data and search trend data about symptoms available for epidemiologists. And there is also a growing ecosystem of open source software for differential privacy, so that you don't need to start from scratch if you want to make use of differential privacy. One of the effort that I'm co-leading in this space is called OpenDP, which is really a community effort to develop trustworthy tools for software tools for differential privacy. We maybe get a chance to talk a little bit more about this during the Q&A, but the features, really the value add we're trying to provide with differential privacy, one is trustworthiness. So implementing differential privacy correctly is very difficult, and we are incorporating into OpenDP a vetting process that really we intend to make it so that the software really faithfully realizes these privacy protections of differential privacy, and you can trust it, and get the community of experts engaged in that. We've built it in a very flexible way so that it can advance with the very rapidly growing science and practice of differential privacy, and that there's a really community governance of this, that it's really a community project where all of us who are engaged in PETs can use this as a platform to share what we learn and advance the field. It's been used in a number of applications so far, and it's really a big push for us over the coming year to find more use cases. So if you are interested in exploring in your organization applications of differential privacy, do get in touch, and encourage you all to join our community. We're having our 3rd community meeting in person in Boston in September. You can join our Slack mailing list and look through our GitHub repository. All right, let's turn over to the Q&A.
Thanks, Salil. Let's take a seat. So thanks for the presentation. And as I sort of preluded before, my intention with some of my questions is to be a friendly skeptic, though Salil knows that I'm very on board with DP and an advocate of DP. But I think it's really important to do that in a way that doesn't just sell the positives, but is really aware of some of the limitations too. So with that in mind, Salil, you sort of mentioned about how DP is an improvement over existing statistical disclosure control that organizations have been doing for a long time. You pointed towards some of the vulnerabilities that they have. But I guess you also mentioned some of the big success stories that DP's had, the US Census, Apple, but those haven't been without controversy in themselves. So I wonder if you could expand on that a bit and talk a bit about some of the limitations that have come out from the early applications and some of the sort of warning notes that you would put to early adopters of DP.
Yeah, that's great. So let me start with the US Census Bureau's adoption of differential privacy. I think we learned a lot watching what the sort of communication process. I think one of the features of differential privacy is that it's it's intended to be something where an organization using it can be completely transparent. So in contrast to traditional statistical disclosure control, the privacy protections of differential privacy don't rely on the methods being kept secret. One of the challenges that the Census Bureau encountered is that the community, that for many, many decades, the disclosure control methods that were being used were not really discussed or known in the open. And so the adoption of differential privacy, while this transparency was thought of as a feature, was provided a shock to the data user community that to the realization that the data was being modified and or noise being introduced to the data for privacy protection, and kind of, I think that was, partly just an uncomfortable realization, and one couldn't make comparisons to what had been done in the past because the protections of what had been done in the past was relying on secrecy. So I think that one is that can be, I think it's important when adopting differential privacy to be aware that that can be a shock to your data users, particularly when it's a context where data, there is a expectation built up over time that data is available in a certain way. And I think we've seen much less resistance in applications where differential privacy is being used to open up new sources of data that weren't available before. So for example, I don't recall there being any controversy about the data being made available during the pandemic from Google and Facebook using differential privacy, and I think that was really welcomed by all. The second bit is I said that differential privacy forces us to confront these very difficult questions about privacy versus utility. And when you have a limited budget, you have to make hard choices about what are you going to publish, which statistics and which uses of the data are most important and deserve more of your privacy budget so that you can those can be done more accurately, and which should be deprioritized. And that can be a challenging political conversation, and particularly in the context of the census, where the data really is used by a very wide variety of stakeholders, and it's a political process to decide where the priorities should lie there. I think, again, in context where differential privacy is being used for a more targeted, focused set of applications, you're less likely to encounter that sort of resistance. Apple, I think that was really more of a function of what I talked about with the local model of differential privacy being one where it's very challenging to get a good place on this privacy utility trade-off. And I think increasingly what's been realized, and people have looked at variants of this local model, something called the shuffle model of differential privacy, or combining differential privacy with other privacy-enhancing technologies so that you don't have to pay this very big price in utility. Because what happened when Apple deployed local differential privacy on our devices is that they set this privacy loss budget quite high because that was the only way to get reasonable utility out of it. And I think now the field has advanced where we've learned from that, and now there's a number of alternatives where you can actually get much more utility, a much better place on this privacy utility trade-off.
Thanks. I think just one further follow-up on the census scenario is that I think we heard a lot yesterday about privacy first and privacy by design, and one of the big promises of differential privacy is that you sort of say, what is the budget I'm happy to expend on this? And you fix that, and then you go from there. So that's my hard constraint. And I think one of the slightly tricky things coming from an organization that does censuses is my understanding of the US Census scenario was that they ended up choosing the epsilon that got the right level of utility that they needed to get the method over the line. And so is that truly a privacy-first approach to using DP? Or does that open you up to potentially the same level of challenges that classical statistical disclosure control has? My understanding is the census used around 18 from memory, whereas in the literature you tend to talk about epsilon being 1 to 10.
certainly as someone who is a privacy researcher, I prefer to think in a privacy first way. I think the point was made in the previous panel. Sometimes there are hard constraints on utility, and I think it is a policy decision which of those constraints is the one that should give. I think for the U.S. Census Bureau, for example, the use of the U.S. Census data for redistricting was considered a hard constraint, because that is the sort of statutory purpose of the first statutory purpose of the census is to enable drawing of voting districts, and you had to meet. They said right from the beginning, this is the fitness for use. This is what the threshold is for fitness for use for that. Now, the rest of the push came because of this dialogue with the stakeholder community, and the truth is that the data users were much more vocal than the privacy advocates. And I think that we collectively as a community need to get more engaged in those processes. I think privacy first can mean two things. It doesn't necessarily mean setting a threshold of privacy first. It means that you need to be thinking about how privacy is going to be incorporated into what you do at the beginning. You can't tack it on at the end. And so I think from that perspective, it was a privacy first approach. But then where the policy decision on where you set the parameters and where you choose to be on this privacy utility trade-off legitimately can come through a stakeholder engagement process.
Thanks. I'm going to ask another question, but I would also like to gauge how many questions there are from the floor before I just fill up question time. So if you have questions in your mind, if you could put up your hand now so I can gauge, and then, because I've got 2 pages worth, so I can keep going until tonight. Okay, so we've got a couple. So I'll go into my main one, which Salil and I have spoken about this quite extensively, so it's familiar territory for us, but it is fundamentally, I think, the biggest thing, the challenge I have when trying to convey why the Office for National Statistics should consider differential privacy. And that's that we talk about it being the gold standard, and we quite often talk about the differential privacy guarantee, and that's very nice in a textbook scenario, but I quite often worry that in the real world, we're communicating DP to non-technical audiences, so privacy policymakers, regulators who are not mathematicians or don't have time to really understand theory. And we're talking about it as guarantees. And the 2 particular scenarios that I sort of have in mind, which I hope are quite interpretable. One is that if you have data that you're releasing that doesn't have differentially privacy applied to it, does that put your differentially private data at risk, or does your differentially private data put that data at greater risk than it would otherwise have been? This is a really common scenario for us because we have Freedom of Information Act requests in the UK, which would just be statistics, factual information that we wouldn't put privacy controls on. The other example is there's strong assumptions about differential privacy about the correlation between records in the data, and there are ways to handle that so long as you know the level of correlations between records. So in a household, in a census, you say, those 5 people live together, they're correlated. But we don't know that my sister lives 5 miles down the road, and then my mum lives 10 miles further down the road. So there are correlations that we don't know about in the data. So I naturally think that we're not in the textbook scenario, and so we need to adjust our language. And so I'd be really interested to get your take as someone who comes from the textbook world, as to whether you think that there's more communication that needs to be done in that space, or whether you're comfortable with the way we already talk about DP.
Yeah, that's a great question. I mean, certainly things get necessarily, even in my presentation, oversimplified in sort of high level, non-technical conversations. So I think it's important that we don't oversell for any of our privacy enhancing technologies the protections they provide. I think the way I think of the benefit of something like differential privacy is that it does have a kind of a well-defined model and privacy semantics associated with it, one that again can be completely transparent. And any implementation of any privacy technology or otherwise is going to be is not going to perfectly reflect the mathematical modeling that we do and in which we kind of analyze privacy. But the clarity of the model that differential privacy provides us with a target that we should be trying to approximate as well as possible. And when we choose to deviate from the model in some way, we should do so with open eyes and recognize and think hard about what the implications of that might be. So some ways in which we deviate from the model, in addition to the ones that you mentioned, is in some applications of differential privacy, some kind of data cleaning process or imputation is done before differential privacy is applied. And that is a deviation from the way that, if you do a really faithful textbook implementation of differential privacy, you have to be very careful and think about what the implications of that are. Doing non-DP releases in addition to the DP releases. So in the context of the US Census Bureau, they release statewide population totals without DP protections, but everything else they chose to do with DP protections. And that was part of the philosophy that because differential privacy doesn't tell us how to reason about the interaction between non-DP and DP releases. These composition theorems are about how the privacy loss accumulates from multiple differentially private releases. We should really try to minimize and only do non-DP releases for the things that it's absolutely necessary to do non-differentially private releases. And so that provides, again, a target. And there is a way to interpret the privacy protections of differential privacy on top of non-DP releases. But by doing these non-DP releases, you could be introducing vulnerabilities. And so you really want to minimize that. And with the last example you mentioned about correlations, I mean, in some sense, this is inherent if you talk about we want protection at the level of individuals, and we want signal about population to come through for larger groups. And so they're really, necessarily when there's going to be a continuum where at maybe individuals or households you have a very strong level of privacy protection. And as you start talking about larger and larger units, those privacy protections are going to degrade because you actually are interested in making sure that you can learn information about communities, for example, which is, it can be the goal. And so some of what you're concerned about, those correlations, the fact that there's correlations in a community, that may be actually what we are trying to learn from our data. And so again, we want to think hard, what is the unit at which I want to protect things, and try to apply differential privacy in a way that's as faithful as possible to that. And that unit can be, as you said, larger than the unit of a single individual.
Yeah. Thanks. Conscious of time, so I'm going to open up the floor because I saw at least a couple of hands. Is there a spare microphone available? Aha. I'm going to vanish backstage momentarily. Cheers. I saw, Jack, you had your hand up, so host's prerogative.
Yeah, so I'm just actually following up on a conversation we had as walking back from dinner yesterday, but would love to get Salil's opinion too, which is, so, I guess you have schema data usually that describes the data, and that might be bounds, or that could also be information about, for example, how many times an entity could turn up in a data set or whatever. And basically that's what tells you what the influence of an individual, or whatever level individual you're talking about, could influence an output. What we were saying is that at a certain point, if you want DP to be ubiquitous, it should be, you shouldn't necessarily need to be like a expert to be, I'm not saying you do today, but we should lower the barrier of entry while making sure that it's very clear and transparent about what people are doing. So is there space, or is there an opportunity to kind of create almost like a roadmap of questions or something that help people describe their data better, such that you can say our DP outputs are guaranteeing with respect to our assumptions, which we can clearly state and communicate to different stakeholders?
Great. Yeah. So I think there is a lot of need for development of user-friendly tools, usable tools for differential privacy that don't require the data scientist to become a differential privacy expert before using those tools. In OpenDP, the way we're thinking about that is that we have our core library, which does require a certain level of expertise to use effectively, but building on top of that higher level APIs or even user interfaces that walk a user through this process of identifying what are the characteristics of their data and the key policy decisions they need to make to use differential privacy in an appropriate way. And so exactly kind of walking through sequence of questions that have to do with confirming the unit of privacy protection. What is an individual's data in your data set? Things that I think over time, as we develop an understanding of these privacy loss parameters in differential privacy, we should be able to translate that to some qualitative descriptions of the sensitivity and risk associated with the data. And so it may be different for medical data versus education data versus e-commerce data, corresponding also to what kind of consent that data subjects have provided. So I do think we need tools that do that. We've been working on one basic version of it, the DP Creator tool in OpenDP. But I think there needs to be a lot more like this, and where as much as possible some of the things are done in an automated way for the user, and then a power user who really wants to get the most utility out may need to kind of open up those boxes and start tuning more knobs.
Any other last questions? Yeah.
Thank you. So fantastic talk, absolutely brilliant. There's been a lot of talk, obviously, today and yesterday on utility privacy trade-offs, and what we're invariably seeing, not from pets vendors and not from pets developers, but from enterprise who are actually using pets, is that they always tune for utility over privacy. They'll crank the epsilon way up high because ultimately, if it's not going to work for them, they won't use it. And so, is there a feeling that people can be, in practice, just kind of privacy washing by saying we're using differential privacy, but they've cranked the numbers up so high that it's not really practically doing anything? And then, I know we can't mandate people to use certain levels of epsilon, but what do you think about, mandating people to disclose what epsilon parameters they are using, and so having an open view on what they're doing? Absolutely,
that's a great suggestion, and it actually was articulated quite in quite a bit of detail in a paper by Dwork, Coley, and Mulligan. They proposed what's called an epsilon registry, which is if a feature of differential privacy is transparency, let's really insist that organizations are transparent about how they're using it. How are they setting their privacy budgets? And that can create some of this force back if this community gets engaged to push back on or to provide the counterbalance to the very vocal advocates of, well, utility is everything. And the reality is that it's not as simple as just privacy versus utility, privacy versus accuracy. There are a lot of knobs that can be tuned. There are choices about instead, I can get more accuracy by choosing to release fewer statistics. And I can get more accuracy sometimes by changing the DP. Actually, this is one that's often probably not part of the conversation. I can get more utility and privacy by changing the DP method that I'm using. And often the conversation stops, I think, too early. There's some off-the-shelf method that someone tries. It doesn't provide enough utility, so they tune the knobs and say we're going to turn up our privacy loss so that we get enough utility. And actually, once we have enough collected examples and a nice repository of DP methods out there, you can actually say, okay, we'll actually try some different methods and see if some of those give us more utility for the same level of privacy.
Brilliant. If anyone has a burning question, I can take one very quick one, and then.
There are more intuitive understanding of what epsilon is. Like if you're going to report it, like you were saying, oh, we've got 80, an epsilon of 80 for the US Census Bureau was shocking to you. To me, it kind of means nothing. Is there an intuitive explanation for it? If you were to say, what's the chance of me, my data being exposed?
Yeah, that's a great question. It is a somewhat challenging one. We in some of the writings that we've done on differential privacy, something called non-technical primer for differential privacy that we worked on a few years ago. We did work through an example where we, in a toy example, illustrate how the epsilon translates to the effect, what, for example, an insurance company might learn about your likelihood of, having heart disease in the next year. What is that change in risk in that kind of inference that they might make based on your participation in or the use of your data in that data release? So one is able to make some translations like that. I think there needs to be more examples of that form. And now, of course, this quantification also can't be decoupled from how sensitive the data is that you're talking about. So if someone learns more about my taste in music, that's a very different thing than learning more about, again, my risk of some disease, for example.
Brilliant. And on that slightly bleak note, let's thank Salil. And yeah, thank you very much.